process scheduler maintains the balance between two conflicting requirements, maximizing the CPU utilization and also providing interactivity by doing context switches in a fast manner between the processes to allow for time sharing on the CPU. So it's the process scheduler's task to pick the available process that will go into the CPU for execution. To achieve this, the scheduler has to maintain several queues. We call these the scheduling queues. You need a queue that contains the all of the jobs or the processes in the system, which is called the job queue. You also need another queue, which keeps this time only the processes that are ready to be executed. So they are just waiting for the scheduler to tell them to go to the CPU. Otherwise, they can just execute their next instruction without any problems. But there are also processes that are waiting for I/O or some event to happen, like for a signal or whatever. So we also need queues for these. Actually, we have a separate queue for each event or for each device, because we don't want one of the devices to block the other, so we need to run separate queues for these. And the processes migrate between these various queues. Like the process could be earlier in the ready queue, then it wants to do some I/O, so it goes into the device queue for that I/O device. When it is done, it goes back to the ready queue, and this time it can go to the queue of another device or maybe another event. So the processes change between these queues all the time. So here we have an example demonstration. Like here we have separate queues. We have the we have the ready queue for the processes that are ready. Let me pick up the eraser to correct that. So we have the ready queue. We have the queue for the magnetic tape. Actually, in this example, we have two magnetic tapes. So since these are two separate devices, you need one queue for each. Or, for example, typically you will not use magnetic tapes a lot, but you will have, for example, disks, multiple disks. So for each disk, you need another queue, because the process that's using, say, disk 0 has to read or write a lot of data, so therefore it would be too slow. Whereas for the other disk 1, you need a short operation. We don't want that long operation, that short operation, to wait for the long one to complete, because anyways, it's not going to use the same device. So why not go with disk 1 while the other process is still using disk 0? So for all disks, magnetic tapes, and all devices that you can think of, the terminals, the printer, whatever, for each one, you have a separate disk. Now, if you look at these queues, you can see that for these magnetic tapes, there is no one waiting. Therefore, these actual linked lists have null pointers. Whereas for the case of ready queue, you have PCB7 as the next one to be actually taken, probably from the queue, followed by PCB2, and after that, nothing. So you have the head and tail pointing to these. Or for the case of the disk, for example, we have PCB3, that means process 3 is waiting for I/O from disk 0, PCB14, and then PCB6 waiting for these. Whereas for the terminal, you have only PCB5 waiting. So this is how you have multiple queues and manage those multiple queues. Now, If you look at the relation of these processes, we can draw what we call a queuing diagram. So our server here that gives some service to the processes is a CPU. So the CPU does the actual thing. Okay, it's either the CPU, a single CPU or multiple CPUs, but again, for the sake of simplicity, here let's assume there's a single CPU. So the processes initially come from outside when first created. They first start in the new state, and then after the new state, remember, they go into the ready state. So when a process goes into the ready state, that process enters the ready queue. Now there could be other processes waiting here. For example, process 7 was waiting here, then we have process 9, then we have process 3, and now we get process, say, 12. So that enters at the very end of the queue. Okay. Now the processes will be taken from this queue one by one. In which order? Could be in any order. That's what we call the queuing discipline. Sorry. The queuing discipline is the way you decide who goes next. Okay. So, for example, if you talk about first come, first served, we'll talk about these later. You will take 7, 9, 3, and 12 in this order. Let's go with that. So 7 will be taken from this queue. So 9 will be the next one to be taken. So 7 goes into the CPU. While 7 is executing, either 7 reaches the end of its main function, so it will leave the CPU and exit the system, or maybe it doesn't end, but for example, it wants to do some I/O, so it makes an I/O request. Therefore, it leaves the CPU. It makes an I/O request. Therefore, it enters an I/O queue. Now, actually, there will be several I/O queues there, but for the sake of simplicity, here we have single I/O queue here, so a single I/O device, and it waits for its turn. There might have been, say, another process here that had come before 7. Okay, so 7 has to wait for 4 to complete. After that, 7 can do the I/O operation. So it will be waiting there for some time. Meanwhile, while 7 and 4 are waiting for this I/O operation to complete, the CPU scheduler will remove 9 from the queue and put 9 into the CPU. So that, for example, when 4 goes into the I/O operation in the I/O device, so it's removed from this I/O queue, and now 7 is at the front of the I/O queue. At this very moment, we have 9 in the CPU, 4 in the I/O device, and 3 and 12 waiting in the ready queue. Now, after some time, 9, for example, completes its given time slice, the time quantum, in the CPU. Therefore, 9 will leave the CPU. Its time slice has expired, so 9 will take this path and come to the end of the ready queue. So meanwhile, remember, 3 has moved here, 12 has moved here, and now 9 is waiting here. Okay? So while this is going on, now for example, 4 completes its I/O, 4 goes into the ready queue. Now 7 can enter I/O device, and our I/O queue is empty, but still 7 has to wait until its I/O is being executed. And meanwhile also 3 is now taken into the CPU, so it's removed from here. And as 3 is executing, assume it forks a child, okay? It says fork. So a child will be created and that will be added to the ready queue. Or the process, for example, 3 could wait for, say, some interrupt. Like you're waiting for a signal from another process or waiting for an interrupt for a device. 3 will start waiting here until that interrupt occurs. Only when that interrupt occurs, it will be put to the end of the ready queue. So this is how the queues are being managed. So if you look at the types of schedulers, there are 3 types of schedulers. The names are simple. The short-term scheduler, long-term scheduler, and the medium-term schedulers. So let's start with the short-term scheduler, which is also called the CPU scheduler. This is the most important scheduler for you, actually, because some of the others may not exist in some systems, but you have the CPU scheduler in all of the systems. The CPU scheduler, as the name implies, is the one that decides who uses the CPU. So it selects the process to go into the CPU and to get executed. So it's that process will be allocated to CPU. As I said, in some systems, that's the only scheduler you have. That's why in general people just say scheduler. By default, everybody understands the CPU scheduler if you don't mention otherwise. This is, as the name implies, it's a short-term scheduler. Therefore, it has to work very frequently. Especially in the case of time-sharing systems, each process is given a very short duration, a very limited time quantum. Therefore, at the end of every time quantum, the CPU scheduler has to make a new decision, another one, another one. It's executed so frequently that it has to be very efficient, and therefore it should be very fast. Typically, the CPU scheduler runs in every tens of milliseconds. Typically, the given time quantum is around 100 milliseconds or less. Therefore, in almost every 100 milliseconds, the CPU scheduler has to run. That means around 10 times every second. If the CPU scheduler is not efficient, then you'd have so much overhead, and then the system is doing just overhead rather than useful work. Therefore, the CPU scheduler has to be very brief and very fast. That's the most basic thing. Now, in some systems, not in all, but in some systems, we also have what's called the long-term scheduler. It's also called the job scheduler because it decides actually on what we call the degree of multi-programming. Degree of multi-programming means the following: how many programs or processes are currently running in the system at the moment. If you have too many programs running at the same time, since you have limited resources, the amount of resource that falls into each process would be limited. Okay? So we want to keep the degree of multi-programming low in that sense. However, if it's too low, now it's possible that those few processes in the system, they all start doing I/O, because it's like process P1 starts doing I/O. While it's doing I/O, process P2 goes into the CPU. But before process P1 completes its I/O, process P2 could start doing I/O. So you also put that in the I/O queue. Process P3 also starts doing I/O, maybe from another device, but still I/O. So you also put it into the waiting queue of that device. P4, soon you may end up with all processes waiting for I/O and no one executing. Okay. Therefore, it's a task of the long-term scheduler to find a good balance between what we call the I/O-bound processes and the CPU-bound processes. A CPU-bound process is a process that's using the CPU a lot. In other words, we have long CPU bursts. A CPU burst is like the process starts using the CPU, and without any interruption due to I/O, it runs for a very long time, just executing CPU instructions, no I/O. Just instructions like add, subtract, whatever, but not instructions like read, write. Okay? So if there is a long sequence of such CPU instructions, we say this has a long CPU burst. And the processes that tend to have such longer CPU bursts and fewer I/O operations are what we call CPU-bound processes. Whereas the I/O-bound processes is just the inverse. They do I/O, little bit of processing, and again I/O. Little bit of processing, again I/O. Now these have longer I/O bursts and shorter CPU bursts. So such processes are I/O-bound processes. Now, in a system where we want to utilize both the CPU and the I/O devices as much as possible, it is important that you have a very good process mix, which means you'd like to have both CPU-bound processes and I/O-bound processes. Now, how much? Is it 50-50 or 30-70? It depends on how much these are I/O or CPU-bound, but it is a task of the long-term scheduler to decide, okay, let me also start running this process because I'm running short of I/O-bound processes, and this process appears to be an I/O-bound process, or the other way around. Now, how you understand whether a process is CPU-bound or I/O-bound, that's another difficulty. We will talk about this later when we discuss scheduling. But that's the basic idea. And repeating again, not all systems have this long-term scheduler. Keep this in mind. Typically, your desktop operating systems like Linux, Windows typically do not have the long-term scheduler because typically we don't have such jobs. The third one is the medium-term scheduler. In the case of medium-term scheduler, now it's like you have taken some processes into the system. These are executing. At some point, you understand that, well, you just exaggerated, and the degree of programming has increased so much. In other words, to put it more clearly, it means there are many processes that you're trying to run. Therefore, for example, most typically, you're running out of, not you're running out of memory, but the available memory, the memory available to each process is limited, for example. Okay? Or there's too much load on the CPU. In this case, you might go over your processes and say, well, I'm going to pick this one, and this one. Couple of the processes as, let's say, victims, and pause them. Pay attention. We're not terminating them. We're not halting them. We're not stopping them. We're just pausing it. Okay? And to open up space in memory, we are taking them from the memory onto a special part of the disk, what we call the swap area, or in short we say to the swap. So we are putting some processes, taking them from the memory and putting them on the swap. Now what happened? I've opened up space in memory for other processes. Okay? So they have more memory space, so they can run easier. And this way, actually, what I've done is I'm decreasing the degree of multi-programming. Why? Because I'm decreasing the number of programs, processes running in memory at the moment. Once again, note that I did not terminate these processes, just paused them. So later, at some point, I'll say, okay, these victims have been waiting on the site in the swap for so long. So let me pick some other processes as victims and put them on the swap and take them back from swap into the memory. So just shuffle them, change the order. Okay? Or maybe I don't need to take something out onto the swap. But anyways, meanwhile, some processes, have already terminated. Therefore, we have some opening in the memory. So bring those in the swap back into the memory. Now, putting things on the swap is called the swap out operation. And bringing processes that were partially executed and now waiting in the swap back into the memory is called the swap in operation. So if you look at this diagram, this sorry. I don't know why my mouse didn't write it. But the second part, the lower part of the diagram, starting from the ready queue, CPU, I/O waiting queues, and I/O, that part is what we already discussed. Now, the medium-term scheduler adds the upper part, which is while executing in the CPU, you decide, okay, let me swap out this process to open up space for the others. So there's a swap out operation. And later, you decide to take them back in. And when you take them back in, you put them in the ready queue, not directly in the CPU immediately. You put them in the ready queue, and at some point, the scheduler, the short-term scheduler, will decide to take that process into the CPU. So medium-term scheduler is not, pay attention, replacing the short-term scheduler. The short-term scheduler manages the relation between the ready queue and the CPU, whereas the medium-term scheduler manages the swap in and out operations. So the medium-term scheduler this way will increase or decrease the degree of multi-programming, whereas the short-term scheduler will decide which of the processes in the ready queue will go into the CPU. That's why it's called the short-term scheduler or the CPU scheduler. In the case of mobile systems, things are slightly different, because for the case of mobile systems, the requirements and the capabilities and the conditions are different. Like the screen becomes a very important entity. Being able to use a screen is important. Typically, you don't have multiple processes using the screen at the same time. Like on your computer, on your laptop or desktop, you could have multiple windows, multiple windows on the screen side by side. So multiple processes are running actually in front of your eyes at the same time. So while downloading something in the browser, you could also be editing, say, a Word file, whatever. But that's not the case in a mobile system, because the aim of the mobile systems, for example, your handhelds, is not to run multiple programs at the same time in most of the case. However, still it has to happen. Like while you're browsing, if a message comes over WhatsApp, you need to be aware of that. Therefore, such systems run in a different way. Also, you have, as I said, you have limited screen space, you have limited processing power, you have limited memory, and you have limited battery power. That's also a concern. So in the case of iOS, there are some user interface limits introduced by iOS. Like typically you have a single foreground process, which is controlled by the user interface, so which is actually currently in the front. That's why it's called the foreground process that you're dealing with. But there could be multiple background processes that are in the running in the background. So they are still in your memory. They're still running, but they're not on the display. So typically they're not supposed to make changes anything on the display, on the screen. And they are limited, like they should have single short tasks. They shouldn't be doing complex operations in the background. Typically, they should be capable of receiving some notification of events like the arrival of a message or whatever. And sometimes, specifically for some tasks, you can allow long-running tasks like the audio playback. But again, it's not changing anything on the screen, but it's at least playing the sound. In the case of Android, Android runs foreground and background processes with fewer limits. So the background processes typically use what's called a service to perform the task. So they don't directly do the tasks, but they do it through the services. And the service can keep running even if the background process is actually suspended. And the service has no user interface, and it requires very little amount of memory. That's how you can actually manage multiple such processes. Now, as I said earlier, the scheduler decides which process goes into the CPU. Again, when I say scheduler, by default, I mean the CPU scheduler, the short-term scheduler. So the CPU scheduler decides who uses the CPU. Now, saying process P1 uses the CPU is one thing. Making C1 go into the CPU is something else, because there is some other process, say P2, already in the CPU. So as we discussed earlier, you should save the state of that P2 process so that it can resume execution later, and restore the previously saved state of P1 into the CPU. This is what we call a context switch, because you're changing the context from P2 to P1 in the CPU. So the context is saved into and restored from the process control block, the PCB. As we discussed earlier, the context switch is overhead. It's not useful work. It's just overhead running. So we would like to keep that overhead as small as possible. The more complex the operating system becomes, and the more complex and larger the process control block is, that context switch will be longer, which implies it will be more of an overhead. So we would like to keep that as simple as possible. The time depends on the hardware support provided for context switch. Some hardwares, for example, have multiple sets of registers per CPU. Typically, for example, if you have two sets of registers, one is the active and the other one is passive. Okay, so let's say this is the active one and this is the passive one. So when you want to switch to another process, you bring the contents of that of the PCB of that new process into the passive one while this is still running. So the CPU is working with this. Meanwhile, in parallel, you're filling this one in. Once this is ready, you do the context switch by saying, now this is the active one and this becomes the passive one. So you just switch who is passive and who is active. So while the CPU is working with this set, you can now start saving the state of the previous process into its PCB. And when it's complete, again, you can start loading the PCB, restoring the PCB of the next one onto this one. Meanwhile, this would be running. Now, when this is ready, then you can again switch, make this one active again, and this one passive, and repeat this process. So this way, you can speed up context switch.